right, so today we'll talk about Twitter scale computing with OpenJDK. Essentially what this talk is why we're using OpenJDK in general, how we use it, and basically our plans for the future as well. All right, so brief architectural overview. All right, so we have thousands of machines running tens of thousands of JVMs. Essentially, it's an RPC server architecture. We have many, many services and teams working together. A service is a team. That's essentially how we scale. We run C. There's some C++, where performance is critical and preferences win. But we are mostly Java and Scala and a little bit of Ruby and Python scattered about. Well, we build and support and own our own OpenJDK distributions and CentOS Linux distributions, and that's essentially we're going to talk about OpenJDK. So, why do we? Okay, a little more about the architecture. This is just a brief overview of how just a little bit of how a tweet is. This is writing a tweet. All right, so we have basically delivery side. We have this just shows the RPC services that we have. TFE is where delivery happens. We do our presentation layer with Macaw Woodstar. We have various services that talk amongst themselves, and then our storage backend. Right? There's lots and lots of services, and it's all hooked together into the finagle backend that is our RPC system. So who are we? So who am I? All right, I said who I am as far as the team that I manage at Twitter. I also chair the Java subcommittee at Spec. I don't know if anybody knows what Spec is, but we write benchmarks. In the past, I was the performance architect at Sun and Oracle. And here I am at Twitter. So what is my team? We hire the best of the best. We have we're going to talk about the JVM team in particular. As we said, we build, support, optimize our own distribution of OpenJDK. And we, as a team, is responsible for backline support of the JVM itself at Twitter. What do? Performance optimization, analysis. We do GC development and optimization as well, C2 development and optimization, and we have engineers from across the industry, most notably those that have done this type of work before: Sun, Adobe, Salesforce, VMware, Microsoft. We are ready to, our team is set up to do what we need to do for Twitter in OpenJDK. So why would we do this? There's actually a lot of reasons why we would do this. And I'm going to kind of, the slides here are pretty, this is pretty self-explanatory. Commercial support isn't going to work for us. Why? It's too expensive. Well, tens of thousands of machines, tens of thousands of JVMs. Commercial software does not have the tooling to even come close to visualizing and understanding what our issues are with that many JVMs in production, let alone meeting our SLAs. As far as what is important to us, the biggest thing that the most driving metric for us is latency. And the typical OpenJDK distributions are out there. As far as their design center for latency, it's somewhere between 100 milliseconds and 500 milliseconds, give or take 50 milliseconds. So what are we going after? Sub 10 millisecond. We want to actually drive it as low as we possibly can. We want to incur no pause from the garbage collector in as far as the life of a tweet, and we're going to do everything that we can to do that. And we can go into a little more detail as far as how we do that now. In OpenJDK now, the way you do that is throwing a whole boatload of memory at the heap. For those, I don't really cover that in this talk, but I have plenty of slides and other talks that we can talk about that for. If you want to have questions afterwards, we can go into that level of detail. Or you can look up my Java 1 presentation from last year. Actually, I went into that in detail. OK, what else? We found that we can support ourselves best. Why? For instance, if we have a dependency on another company, if Twitter has an issue, garbage collection takes a service down, or there's a crash that takes a service down, who do we call? Well, think about it. You call a company, they give you their 2-hour response time. They have an issue where they have to get the backline support. We don't have to deal with any of that. Essentially comes to me and then goes to Karen Deep, sitting there in the front. See, I told you. So more or less, we have control of that. Are we going to solve all problems? Yeah, we are going to solve all problems. We have the staff to do that, and there hasn't been any issues that we haven't been able to address thus far. OpenJDK development process is rather slow. Now, this is not the fault of the team. I used to work with that team for many, many, many years, so I'm not going to throw them under the bus by any means. But when you're working in a community, when you're trying to get everybody to agree with what's best for everyone, things are slow. There's no way you're going to have that slow, have that fast. So the development pace is just mind-numbingly slow for a place like Twitter that knows exactly what we want to do, and we can just do it ourselves and deploy it. So that's essentially, that's what we're doing. And it is an eternity until new code is support. Eternity, as far as the way we define it. As it stands now, if you want something new in OpenJDK, it's targeted for JDK 9. If you know somebody, maybe you can get into 8. But that's not. That's their model. That's fine, but it doesn't work for us. So we've decided to do something different. We need custom tools that we can run into production. We need to be able to identify what is causing that 15 millisecond latency or that 20 millisecond latency, and not only do it and do it now in production, not give me a reproducible test case and we'll do it offline. That is not an option for us. Yes, mission control is an awesome tool, but it won't work for tens of thousands of JVMs visualizing, as far as aggregating that data and telling us what is happening with our data centers in general. It just doesn't do that. Low latency garbage collection in OpenJDK is long overdue. It hasn't happened. As I mentioned before, it's when you try to look at what is best for everyone, those corner cases don't really bubble to the top. And low latency garbage collection from our point of view, meaning 10 milliseconds or later, is not, in our view, on the horizon. So we're trying to take that into our, we've taken that into our own control. HotSpot is not optimized for Scala. Yes, HotSpot is very optimized for Java, but it is not optimized for Scala. We write a good chunk of our services in Scala, and that leaves a lot of low-hanging fruit on the table. For instance, let me give an example. Autobox elision is a good example. In JDK 6, I believe, I could be dating my, yes. Autoboxing happened when you basically would give a class that would take an object automatically. Everybody knows what autoboxing is, right? So that happens without you realizing it. It happens pervasively across all of your applications, and you basically get a whole boatload of more allocations than you may even have control over. In Scala, there is very little control. That just happens. In Java, you have the ability to understand where that is and maybe manipulate it a bit, but that doesn't happen in Java. I'm sorry, we just don't have that visibility in Scala. So we need to implement autobox elision like we've done even more extensively in Java in Scala. So that's a good example. Our designs, the OpenJDK Design Center and ours don't match, right? We run massive heaps, and we require very low latency, and that is just not, we're not aligning. So we have to, that's another reason to take things and do things differently. And the current tooling in HotSpot, this is the, what's available for free in OpenJDK is, well, it's limited. There's not much there. It does leave a lot to be desired. Spartan, as you would say, guaranteed. Right? So how do we do it? OK, so first of all, mostly, as we stand right now, we are mostly, as far as looking at the line counts and how many changes we've made thus far, are purely OpenJDK. We do have modification add-ons that we primarily have there for observability. So we've enhanced GC logging. We have additional information now. We have additional parsability to the logs. And we've greatly enhanced the observability, what's available in the beans as far as JMX beans and what's available. GC details is there. We have an understanding of what the safe pointing happens and how that impacts operations in the VM and the timing and turn. Safe pointing is actually a very good example of what is not observable now in HotSpot. It is a pause that happens. It happens more frequently than you think it is. And when you're trying to identify all those 10 millisecond pauses that happen, safe pointing very quickly bubbles up as an unknown. So we needed to understand what was happening there. And most of the code is internal to Twitter right now. Our philosophy is to make sure that we have very good stuff that we can use in production. And then once we are ready to do so, we will open source it. We have several, actually 2 specific projects that we're working on now that you'll most likely see shortly. OK, our repository management. Our OpenJDK sources are based on HG OpenJDK Java.net. Our current code base is JDK7 based. That's 1.7 update 60 build 12. We also have a future code base of JDK 8 that we're working on. We maintain the Git clones of the Mercurial repositories. It's here listed here, plus Nazorn for JDK 8. Okay, mirroring OpenJDK. We clone each of the repositories. Git doesn't support Forest as Mercurial does, so these turn into 7 Git repositories. What else here that's interesting? Okay, so HEGit is rather slow. So we use experimental performance versions to parallelize this effort. It seems to be working pretty good for us. The local Git branch contains the exact copy of upstream, and then we integrate our change sets to it, and then finally we sync master branch to the internal GitHub. All right, so this basically goes through the very specific processes. I can walk through this, but let me just cherry pick a couple interesting points. All right, so as far as our modifications are concerned, where does he cover this? Right. We're trying to keep our changes in the source closed and try to leverage that mechanism that's currently in OpenJDK. It's primarily leveraged by Oracle for their closed implementations and closed features. We'd like to do the same, and we're trying to figure out how to do that now in the OpenJDK. Essentially, what that will allow us to do is have our own stuff separate. We can pull down from upstream and then merge after the fact. Yeah. So our big effort right now is this has been a very large effort for us since I've joined. Keith McGuigan is on our team has been leading this effort, and it's a night and day change than what we had in the past. Our cadence, we release monthly, right? So that's clearly a big change, right? We do review and verify all CVEs. We will pull in a release and release more frequently if we need to. It really depends on the severity of the CVE. We do a 2-week limited. So we have our own testing, which I'll cover as well. But we also have this notion of what's called a canary. A canary is live, limited test deployment. Essentially, it's handling live load. Is it actually delivering tweets? Yes or no. It's the single best functional test that we can do. Handling this is our code running. Let's see how it does for 2 weeks. Right. Once we're done, it's moved to production, and we coordinate with service owners to verify that it is stable, which we usually see out of the canaries as well, but also from a performance perspective as well. All right, here's a nifty graphic kind of going over this. All right, as you can see, on the left-hand side, we're pulling from HD OpenJDK Java.net. We bring it to our local machines at Twitter. We do the translation between HG and Git. And then we do our merging in our own Twitter Git repo. Right. So this is a pretty big. So let me see. Yeah. Okay. We'll finish this section off, and I want to just open up for questions as well. All right. So additional files. We have certificates. We have a perf agent that we've made modifications to. There's a tool called Heapster that we include as well. We've changed our version strings just to be able to match how we are going to release. And we made some modifications to aid in observability tools in GDB, perf. One example is restoring the frame pointer register. And we've added a null character for internal strings for symbol ops. As far as the operating systems that we support, compared to Oracle and IBM and the other vendors that work with JVMs, we support CentOS 5, 5, and 6. That's it. So that certainly simplifies our problem as far as what we need to deal with. We custom build the makefiles to invoke OpenJDK makefiles to require the parameters. And then we use Puppet configurations to deploy to our Yum servers internally. So we talked about that testing. So we have our own automated performance regression testing system that we do our testing for HotSpot and JDK repositories. It does use JT-Reg. Clearly, we want to make sure that we're not blowing out as far specification and as far as running pure Java as best we can. And we do performance measurements with some of the spec benchmarks. We do have there are more benchmarks than this, clearly. Me listing a bunch of bird names is not really going to mean a lot to you, right? So let's just say there's a lot of birds that we test as well. We do the internal deployment, the canary system as well. One of the biggest things that we've implemented is a complete heap profiling solution that we enabled in production. This is allocation profiling. And it does it by sampling T-labs and as far as the fast path. And it also will do a complete profile of slow allocations. Slow allocations don't happen very often. But when they do, you kind of want to know absolutely everything you can about them. So that's why we do the complete profile. This tool also does tenuring profiling. That's survivor spaces and old P-labs. The survivor space is what's copied back and forth to, as far as what makes an object survive. An old P-lab is where those objects are copied into in the old generation, so we can understand what is being copied back and forth between survivor spaces, and then in turn what is promoted and tenured in the old spaces. We do both of those by sampling. As far as deep heap profiling is concerned, this is complete full path profiling. In CMS old generation, we do complete profiling. It's concurrent. It happens during a CMS cycle. The rest of the heaps we do complete during a full GC. CMS is the collector that we're most concerned about. I mean, as far as the one that can somewhat guarantee low latencies effectively is CMS. There's obvious failure conditions for that collector, but we've found ways to mitigate those problems. I have high hopes for G1. I'm still hopeful. So we'll see what happens there. OK, so what's included in the profiles? So there's essentially two basic, there's a basic class histogram, and then there's a more advanced extended class histogram. What we have enabled in production now on all of our JVMs in production is the basic class histogram. Our overhead is less than 1% for this work. What we give is a class name, size, counts, the heap space, where it is, whether it's in the Eden, the survivor, the old space, what activity is happening in that regard. And again, this is very light overhead. There is not so as you can imagine, as we thought about building these tools, when you're trying to get a handle on latency, and the biggest thing you have for any Java program, Scala program, is to get a handle on allocations. That's what impacts the rate of promotion. That's what impacts garbage collection. And we had no tool that we could actually effectively do that in production. This is why we built this tool. And yeah, so a bit more further, there's an extended class histogram functionality as well. This is not on by default. This is you can turn this on by it's a live configuration. It doesn't require restarts. It includes first level reachability information, basically what objects are pointing, its references to and from regions to other classes and other spaces, and it's grouped according to heap space size. It is 3 to 4 times more expensive than the basic class histogram, and it isn't on by default, but it can be enabled dynamically. So essentially, the flow for this is that any one of our services, any one of our JVMs running in production, we can attach to and get this level of information. I can actually break to that right now. So quickly here. So this is actually the output from this tool. All right, so let me back up and give you the value add for this again. We run into an issue in production. Hey, why are we running into this garbage collection problem? Our first thought is allocation, increasing allocation. We verify that if it is indeed increasing allocation rates, what is allocating? This benchmark right here is spec JBB 2005. I don't know, it's very easy to run, so that's why it's here. In that benchmark, clearly, right here you'll see this is character arrays. So it's allocating a whole boatload of character arrays. Okay, but it's also allocating character arrays in the slow path allocations, as you can see here, but there's only one of them, so that's not too terrible. What's next is string. You probably can make the correlation that the backing character arrays are of strings. All right. Okay, so tenuring information. Oh, actually up here. So this is a sampling profile. The interval in which we tested is between 2.73 seconds and 3.2 seconds. We scanned 648K of the T-labs and that's 0.56% out of the total 113 megabytes in the T-labs at that point in time. And it took us 30 milliseconds. and a TK footprint. So yeah, same information for the tenoring profile. Notice as well that it's again, it's the character arrays that are being promoted. Okay, that's at age 1. Actually, I'm sorry. Let me back up a second and go through some more detail. So the tenoring profile is telling us what ages in which we see these objects. So in age 1, it's not surprising that we see the character arrays here because this is the first, garbage collection. This is the first copy, the first age. As time goes on, we see that that clearly changes. However, we do have a whole boatload of strings and character arrays still surviving well past into age 5. Potentially a problem. Okay, now this is the extended profile. And you can see my notes here. Right, so as you can see in my notes here, the highlighting string is pretty interesting in this regard because, all right, so let's take a look at, okay, this is character arrays. Okay, we see all the references from R to Eden right here. Same thing with this one, integers. From, oh no, this is the next one. Let's go down to string. Okay, string is in Eden, but right here you can see the references to that this right here, the character arrays are in old. So we have the strings still in Eden, but the character arrays that back them are in the old generation. That's, not many tools that can tell you that level of information. All right, so this is just a full class histogram at this point. It tells you what's alive and what is dead. This is gathered before the full GC actually happens, so we can actually find out what is dead and what is live. Why do we do this? Well, it's an interesting. We're trying to get all the information that we can. But there's also this notion of this effect called nepotism, where you have objects that have died, that are referenced, died in the old generation that are referenced from the young generation. And since an young generation referencing dead objects in the old generation, they cannot, it can't release that reference until the old generation objects are collected. So you have these essentially dead objects in the young generation that are kept around, waiting for the old generation objects to die. And they don't get cleared out at all until the old generation dies, and then the rest of them get cleared out. This tool and this information here tells us just that when it's happening. What you would see is down here is, actually here it is right here. You see that string object here. Well, no, you would see a string object here in the young generation, or in the survivor space, pointing to something in the old generation that's died. But I don't have that output here. But that's essentially why one of the reasons why this tool has been built. Okay, any other questions about this tool? Go ahead. So the question was, do we work directly with developers, helping them understand what they can do to impact garbage collection and other effects in the JVM? Absolutely. I mean, the single biggest thing you can do to impact the performance of a Java, any program, is to it's top-down analysis, right? Manipulating the algorithms and the code itself. The JVM can only do so much with what it's handed, right? And if you have code that's poor or not inherently inefficient, the JVM can't remove inherent inefficiencies from your algorithms. There's just no way we can do that. So the way my team is set up is that I've got a VM team and a performance team. The performance team's job is to identify what aspects that we can optimize in the JVM itself, in the kernel itself, but also work with the service owners to identify what can they do at the service owner, from a service owner level. So it's both top-down and bottom-up analysis. And it's the top-down analysis where we go and work with service owners, identify what are those patterns in the code, what are they doing that impact the latencies or other metrics that are a problem. Yeah. So the question here, I'm sorry, I didn't repeat the question, was, so we don't like immutable objects, and collections in Scala. Yeah, it lends itself to high rates allocation. There's nothing we can do about that, right? I mean, that's absolutely right. Can we avoid that? No, not in that language, but not that I know of. So that's where optimizing the JVM comes into play, we'll cover some of that we're going to. So this feature right here, this tool right here, will be open sourced. We're in the process of going through the internal review for this now. Yeah, we plan to give this back and Hopefully it will be accepted by the community and everybody can use it, which would be awesome. Okay, let's see here. All right, so one of the next tools that we've modified is perf. So why perf? All right, so what we were looking for is a global dynamic arbitrary context kernel and user mode instrumentation. What is this? Essentially what we're looking for is a view from the lowest level, from the code that we generate from the JVM, the machine instructions, all the way up to the highest levels of the stack. Not only the machine instructions, but also what is it doing to the kernel, and what is the kernel doing. We need to see everything that's happening. And we also need extremely low overhead because we want this to be enabled in production. We want to be able to go to any of our JVMs running and give us this level of information. We also want to be able to execute arbitrary actions when an event occurs. For instance, if we see that we have, we see an increasing rate of allocation or increasing rate of promotion. What can we do there? Can we turn additional tooling on? Is there things that we can do to mitigate that issue? So that's essentially what we're looking for. What's in HotSpot now? Okay, so we got JVM TI and JVM PI. Reasonable interface to get information, but it really is just Java and above, right? Nothing more. It just gives no observability into the JVM. There's dtrace trace points riddled throughout the JVM. So that's awesome, but there's not a lot of use for that except system tab we can use now, but dtrace is not terribly useful at the moment. And also there's in-memory metadata and data structure layout through its serviceability agent. So how can we tie this all together? And that's Linux perf. So perf is just a Linux profiler, right? It's an abstraction layer over the CPU performance counters. So you can see here, this is basically all. This is just a perf as far as the output, as far as what it can do. You notice that it's got a lot of tools. If folks have I kind of correlate it to the performance analyzer in some ways. I mean, it's got some aspects of that as well. And also, there's a pretty nifty view as far as a top view of what's going on to your process. Okay, so yeah, here's just an example output. Notice that we see the Scala level code, and it continues to go down as far as to the lowest level. So I kind of clipped it at this point. And it has some observability into what the JVM is doing. This is a vtable stub. This is a virtualization. This is it's a polymorphic call. And polymorphic calls, you end up going to the vtable. Why perf? Perf is very powerful. It does the mixed mode stacks, aggregates stacks of any CPU performance counter. If we want to see TLB misses, we can aggregate on TLB misses. If we want to see L2 cache misses, we can do the same. Path length, anything that the CPU can give us. It also has an attached spawn and top modes. So it was pretty clear that it made sense to do this, especially since we only were worried about CentOS 5, and 6. Pretty straightforward. So what are we adding? We've added Java tracing to perf. It's got much more richer context-specific data, and it's all on a unified event bus. So essentially, this is just a graphic saying what we're doing. So we can take Java, Ruby, Scala, Python, native, Linux kernel trace points. It's all dumped into the perf event stream, and then we can read it out by either recording or viewing it in production on the fly. Right, so with this tool and with the framework that we have, we can do things like, I mentioned that we can, in a face of an event, we could do some action. So if we say, hey, start turning on profiling, start turning on information, or start gathering stacks when we see latencies greater than 20 milliseconds. So if we see latencies greater than 20 milliseconds, we start recording. When that happens, we see just the transaction that took more than 20 milliseconds, and we can see the entire view from what happened at the machine level all the way up to the highest level of the stack, and that is just what happened above 20 milliseconds. It's the perfect tool for us. This is not open sourced yet. Both of these tools that are in process. This one requires kernel level changing as well. So 2025, we might see it. I don't know. It just adds, it's not clearly as easy to do it as we would do in Open JDK, but we're certainly going to work on it. When it comes down to, from our perspective, we see no reason not to open source things. There's no inherent reason for us to keep things closed. In fact, it's better for us to open source it so we don't have to directly support it. We can just let the community support the issues. So any of the things that you see discussed here, yes, we want to make sure it's high quality. We want to make sure it's useful. We don't want anything to open source that's half-baked and not really finished. But once it's finished, we have full intention to open source. Other tools. OK, so I talked about the GC profiling information. We have advanced CPU profiling as well. It has safe point statistics. We can track times for each VM operation type. We can initiate GC minor collections from Java. So Java code can actually initiate a minor collection on the fly if we so choose to do so. And we have command line tuning parameters for GC log rotation, which I think is actually not correct anymore. Future work. We're in the middle of a transition to Java 8 now. There's a lot of developers here internally that want the goodies of Lambda and the new collection of libraries. So it's a big thing for us. We're working now to engage the community in open sourcing our code. So we'll start to see, we have JEPs in internal review now for some of the projects that I just discussed, and other little ones, and smaller ones as well. So you'll start to see as we start to trickle those out, you'll see those as well. The idea of externalizing internal libraries, yeah, I mean, I think that's something that we would consider. If we can't open source them effectively, might as well give the code out in other ways. I don't see there's any reason to not to do that. We will continue to advance our observability work. As I said, it's one of the biggest gaps that we have in Open JDK now. If we're able to actually be effective in providing tools that allow us to do our work here, we feel that it probably help you guys out too. So it makes sense for us to get them out there. Some of the things that we're considering as more parsable output logs, maybe binary. So, looking at garbage collections, for instance, every time the output changes, as it changed in Java 8, everybody's rewriting their parsers over and over again. I can't even count the times I've rewritten a GC log parser. So one thing that we're considering is rewriting the backend for logging to make it binary and maybe a JSON interface so we don't have to rewrite our logs. So yeah, that's awesome. We feel the same way. So that's actually a big effort for us now. And we kind of view it as a reliability thing because we can't see, I mean, having difficulty with tools makes us miss obvious problems. And that's frustrating and annoying, and we have to find ways to get that additional insight into what the garbage collector is doing. So we're going to take it on ourselves. And tighter integration with the Linux perf framework. So as you can imagine, perf framework is its own unified logging backend, right, from the OS level. And if we build something from the JVM, it's just a natural extension for them to be very closely coupled together. And more testing and more benchmarks. So we want to extend our tests as much as we can. And DeCapo has a Scala port, and we've been looking at that as well, which is pretty interesting. Low latency garbage collection. So I kind of hinted that this is a big problem for us. So we actually have two projects in flight right now. One is called an intermediate generation. And the second is a thread local garbage collector. So intermediate generation, what does that mean? So OK, so there's a lot of people who use caches, and these caches don't stay around very long. Say they stay around for 5 minutes. All right, so you have a cache that stays around for 5 minutes. You allocate it in the young generation, and then you copy it back and forth, back and forth, about 15 times until it goes to the old generation. Okay, so what the intermediate generation will say is, granted, it's very early prototype right now, and I'm going to demo that in a second here. Say this type of class will last for 5 minutes. We know this class is a cache, and it'll be around for 5 minutes. So when it goes to promote it, it drops it into the intermediate generation. That's bucketed for 5 minutes, and then it just sits there. So there's no copying back and forth. There's no scanning of the old generation every time we have to look at stuff that has that additional overhead to see if it's live. It doesn't come eligible to even be looked at until that 5 minutes is up. Then it comes back in, and we collect it, because we know at that point, well, clearly, we're going to treat it like any other object, but we know from the design of our application that after 5 minutes, that is dead. So that one next scan is scanning dead objects, and it's just evacuated from the heap at that point. Thread local garbage collection. This is an interesting one. Myself and another one of our engineers at Twitter that came from Sun, Tony Prentizis, many times in the past have thought of thread local garbage collection as not possible for OpenJDK as a platform in general. So why? Because in order to actually make so that's basically treating everything initially as thread local, meaning that it's only be accessed by a single thread. And if you don't know really what's happening to that object, the machinery and the mechanisms necessary to handle that as a thread local allocation is insanely difficult, because we don't know what's actually happening. You have to make sure, you have to check for globalization events, meaning that what happens when it's globalized, being accessed by other objects, and it ends up being that the mechanisms and the machinery necessary to make this work for everybody is nearly impossible. So we've killed it many times. It's come up 3 times that I can think of in the past 10 years. So why is it on my slide right here? It's on my slide right here because we have control of the entire stack. We can actually manipulate an API saying transaction begin or tweet enter, right? And at that point, we know that's the scope of a single transaction. And we can say exit at the end. And during the scope of that single transaction, those objects are, most of our services are indeed stateless. So most of the allocations are going to be thread local. In fact, we know that in most of the worst cases that we have, 91% of our allocations are thread local. So it's perfect for a thread local garbage collector. So a thread local garbage collector will essentially say transaction begin, allocate thread local, meaning that all allocations will be local to that thread. We do nothing until the end of the transaction, and then we throw it out. Right? So pauseless for the scope of a transaction. And we're building that now. We're also going on targeted optimizations for Scala. What is that? I talked about out-of-box elision, but Scala is, there hasn't, well, to be very frank, the JVM is very, very tailored for Java, very specifically tailored for Java. In those cases where it's very specifically tailored for Java, it's going to fall on its face for Scala. Where does that happen? Inlining. Inlining is really the entry point to all advanced optimizations in C2. And inlining is gated by the size of the objects and how big the inlining scope would be. Scala is going to be 2x, 3x, 4x as big as what Java would be. So if that happens, only a fraction of what we can do in Scala is actually inlined and optimized. Simple things like that. We haven't even, that has not been considered for HotSpot and Scala in the past, and we're going to go down that path. OK, let's go into our demo of the intermediate generation. OK, now so whenever I demo anything that's from HotSpot, I can't say it's the sexiest demo in the world, so I apologize. So I'm going to run spec.jbb, and we're going to look at output. All right, so right here, this first one is no intermediate generation. So I'm going to run it through a little bit, and I'll describe what's happening. This is JBB 2005, an incredibly simple benchmark. It has a relatively high allocation rate, and it's really easy to run. So here we are. So it is running right now. So what it's doing right now is a warehouse is a thread. It's going to run 6 threads, and it's running its workload. You can see that it's doing a lot of allocation. There's a lot of young generation pauses. And it continues. And notice the size. It's getting up into about 250 megabytes at this point. And timing's not too bad. We're looking at 1,200. Yeah, there you go. All right, so now we're changing again. Now our footprint is up into approaching 400 megabytes. I'm looking right here. Over 400 megabytes. OK, we're going to need another phase change shortly here. OK, look, there was the first initial mark. That's a CMS. OK, so now the CMS is going to start actually doing some work at this point into the 10th warehouse. OK, so now we're old generation's happening, right? So our footprint's up in the 400 megabytes, and it's doing some work in CMS. It's still around 400 megabytes. CMS is relatively active. And OK, we come here, and there's, OK, our score, 113,000. Well, not the score doesn't matter. But OK, so let's go down over here. I'm running the benchmark clearly modified. It takes about an hour to run in an unmodified sense. This is a one intermediate generation. OK, this is an intermediate generation of one for just 2 seconds, right? So it's those very, very transient objects. We're going to just hold on for 2 seconds and see what happens. OK, so immediately you can probably see that the rate of garbage collection is quite a bit slower. And our footprint is it's similar at this point. It hasn't really changed. But the growth of the heap is relatively small. It is quite a bit smaller. All right, we're going to get a change to the next warehouse at this point. Same thing. Each warehouse has a fixed about 2 megabytes overhead from the static footprint is concerned. The rest is transient allocations that are being promoted into the old generation prematurely. Essentially, they're objects that will die that are put into the old generation. Still, we're at about 300 megabyte heap. OK, so here we are. We're in the last. This is warehouse 10. We haven't CMS'd yet. Footprint is approaching. It's getting higher. Still no CMSs. And we're going to end this workload without a single CMS and quite a bit higher throughput as well. So just a note, as we scroll back here, you can see our footprint ended at 459. More or less the same, right? So footprint's not too much different. It's where were those objects and what were they doing, right? The objects that were held in the intermediate generation did not have an impact on the heuristics of CMS. CMS was not triggered prematurely. OK, this is not too much different. OK, this is basically a two. This has two intermediate generations. One with a timeout of 2 seconds, one with a timeout of 20 seconds. This is taking basically all objects that will bucket into these at this point. There's no mechanism to say this particular object will last this long at this point. This is just really early prototype. Again, it's just ripping through here, and we're not going to notice too much difference here, but even it's a slight footprint change. OK. Right, so what this effectively does for us is that we have those caches that we know are going to be around for a certain amount of for a contained amount of time, not forever. It's not up to the application or up to the user to determine. We have them because they're cyclical caches. We know they're going to be live for a certain amount of time, and then we'll get rid of them. It's extremely powerful to be able to avoid the garbage collection overhead for those situations. So just scrolling back here. OK, it did not have, this is pretty striking right here, footprint. It's 100 megabyte difference in footprint by using the intermediate generation. And pause times, we never had a single CMS throughout the length of the pause time. And as far as the performance of that particular warehouse, this one's 144. This is 133, significantly faster as well. From a throughput perspective, right? So because we're able to avoid those pauses that impact. So CMS is concurrent, right? So it's not really impacting the flow of any particular mutator, but it is impacting the performance capabilities of that mutator and its influence on the processor, right? Caches such as last level caches or CPU caches are going to be dirtied by a garbage collector that's sweeping and moving through the object heap instead of keeping just the mutator threads doing their work warming caches. That's the effect here that we're seeing performance-wise. All right, guys, that's it. So thank you very much.